Hello, I'm Wesley Wooden.
I'm Arson Brossett.
And this is our microgrid project for Power Systems ENGE 270. And our town is Barra Roja, Madagascar.
So the purpose of this project was to design a power grid for this rural village in Africa, and then physically build a micro power grid to model and simulate, which you can see right here in front of us. Our design team focused on this small river town in the central southern area of Madagascar called Barra Roja.
As you can see, Barra Roja is right here and it lies on a river in Madagascar. So our design had many constraints, as can be seen, but only 4 were very important in how we implemented and designed this. One being that we had to have 7 unique loads. To do this, we had an inductive load as a refrigerator, we had resistive loads of ovens and electric stoves, and we had lights and also capacitive load that is power chargers, phone chargers that are in the huts, because power and phones are becoming very important in third world countries. We also had to include several times of day and be able to show the balancing through those and maintain a power factor of at least 95%, which is done by balancing the inductive loads with capacitive loads and balancing capacitive loads with inductive loads.
So as we mentioned before, Barra Roja is located on a river. Now this is perfect for hydroelectric power, which is one of the most efficient, reliable, clean power sources, and which would be a really realistic power generating source for our town. As we can see here, this is the average rainfall over the year, and this being the average, this is like a max year, a kind of low year, and you can see there is always rain falling throughout the year. And here you can see the number of days through a year which are half the rain.
Here's our general arrangement of our power grid. As you can see here, there's 2 houses that are in phase, another 2 houses that are in phase, and a marketplace that's in phase.
Now in each house we got LED lights, electric stoves, and a phone charger. There's all 3 of those components in each of the 4 houses, and the village market has 2 LED lights or more LED lights, 2 electric stoves, and 2 fridges so that they can store and cook food for the rest of the village. So here we can see the more intricate design of our microgrid. Here's our generator, which will generate our 3 phases. Got the marketplace, which is on one phase, hut 1, hut 2 on another phase, hut 3 and 4 on another phase. And here are our correction factors. So for the houses, we have inductive loads, which would help balance out the capacitors being used to charge our phones. And in the marketplace, we have a capacitive load to help balance out these inductive loads in the refrigerators.
As you can see, we have resistors modeling ovens, capacitors modeling phone chargers, and then inductors modeling refrigerators,
as well as resistors and LEDs modeling the lights.
Now, currently, Barra Roja doesn't have any power, and almost only 10% of all of Madagascar has access to power. But if our power grid was introduced to Barra Roja, it would provide efficient power for lighting, phone charging, etc., and overall improve their lives. Our system provides smart balancing, allowing for what we've previously mentioned of balancing inductive loads and capacitive loads by introducing capacitive to inductive and inductive to capacitive.
So again, given the town's climate and location, hydroelectricity is logical and sets our design far apart from other potential power grid systems. Here we can see an average rainfall of the national rainforest, which is a national park right near Barra Roja. And our system will provide near constant power throughout an entire year at a high level, potentially decreasing during these 2 months seen here during beginning of summer However, there's still going to be a flowing river through the town.
As previously mentioned, the energy will be clean and efficient too because it's water.
So a small hydroelectric power generator could be easily installed close to $10,000 and provide about 50 kilowatt hours of energy. The manual labor and maintenance for this is not terribly high, as there's mainly one moving part and the installation takes roughly a week or so to install. Maintenance only has to be kept up every 10 or so years on the hydroelectric generator, and extra generated power could easily be stored in other forms such as pumps, raising water up to higher elevations we drop later, or batteries. And unfortunately, we're not able to currently implement this into our microgrid, as this is would be needed as a future advancement later on down the road.
In addition, we could also add streetlights to our grid, which we didn't include, but it could be an addition that would improve the daily lives of the residents of Barrio Roja further than what we've already done.
So initially, our projected load caused our motor, which is supplying our generator, to fail when we started it up. This was due to our load drawing more current than we were expecting. This was fixed when we altered the load and increased the current supply. In our practice, our generator would underperform and not supply enough to our loads if this were to happen.
This would result in power outages, lights being dim, phones not charging, etc., which is actually a big problem in a lot of places that are trying to implement grids like our own currently. But overall, our grid succeeded in showing that we can balance power in a small village and create loads that don't ruin their generator and can be efficient and sustainable. Thank you.